Hello, guys. So this is Matheus, and I'm here to present the paper that I chose for this week's paper club, which is BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding, which is a paper that I think it was interesting, with all the hype regarding, ChatGPT and stuff like that. And I think BERT was really a very important work in this field of NLP, because when it was released, like, it really achieved state of the art on many tasks. And I think it was kind of the basis for this revolution that we have, and also if you think about BERT, if you look at Google Scholar, like, the amount of citations that this paper have is really like it's 50,000. So it's really like the guys like to cite this paper for some reason, but I think it's because especially of how groundbreaking it was, even though maybe like it's outdated now, because the paper, like here you say 2019, the paper is like really 2018. So we have like 5 years or kinda, but also it's kind of really interesting to think that 5 years, this was the groundbreaking things, and now 5 years later we have this, that people say, oh, it's superhuman, ChatGPT can do lots of stuff. So I think interesting to see that. This paper was released, by the researchers from Google, and then here, and here I will present the paper, the highlight parts that I think are interesting to discuss on the paper. So basically here, the researchers of Google, they say that they released BERT, which is like a model that, it uses these bidirectional encoder representations. So they argue here that this bidirectional part is really important, and also usage of transformers. And in this release of BERT, they achieved really state-of-the-art on many tasks, so like GLUE, which is like a set of language understanding tasks, Squad, which is question answering, and stuff like that. Yeah, I think that's basically it for the abstract. And then in the introduction, they start talking a bit about, this language model pre-training, which is, I think, also to give context here, also we have in 2018, OpenAI released the first version of GPT. So we know it now have like GPT-3, maybe ChatGPT, maybe another version, but at the time of release of this paper, we have GPT-1, and BERT was released a bit after that. But then they argue here first that the language model is being very useful for training, especially for more complex tasks. So here they say paraphrasing, question answering, and stuff like that's not really at talking level, but then you have to understand like maybe the context of the words, right? And then here they say that there are two main different strategies for applying these pre-training representations, which is the feature-based and fine-tune. And then feature-based, they talk here about Elmo, which is, I think, like, if you understand a bit, is where BERT comes from, and Elmo, I guess the name is comes from Elmo. BERT was named because of Elmo, I suppose, which I'll talk a bit later. But basically, you have like these representations, you fit that on your data, and then you have some representations. Elmo is kind of interesting because instead of like a word-to-vec approach, which you have a embedding for each word, Elmo, you give an embedding, give you the context of the words that surround it. But basically use these embeddings, for a downstream task. So like, question answering, sentiment analysis, etc. And then you have this fine-tune approach that they say here. And one example, they give this generative pre-trained transformer, which is what GPT stands. So I don't know if you guys don't know. I don't really remember why, but GPT stands for this, which, they pre-train this model on a large set of data, and then they fine-tune all the parameters for the downstream task. So one of the limitations that the authors of this paper rise is that they have a limitation that is because of the choice of the architecture. Because, for instance, like the OpenAI GPT, the authors use this left-to-right architecture. So, you only see the tokens that come behind of you. You don't see the tokens that come after. And then you apply, stuff like self-attention and attention from transformers. And they argue that this can be a limiting factor. And I think it makes sense, right? Because if you think about translation of the words, you have languages like English and Romance language, etc., where you have like is subject, verb, and object. So I ate an apple. And then you have languages like Japanese, which is SOV, so it's subject, object, verb. So I ate an apple in Japanese would be like watashi wa ringo o tabemashita, which is kind of like watashi, I, ringo, apple, tabemashita, ate. So kind of it really depends on that. And also have other languages like instead of English, like Portuguese, that have gender. So have articles must agree with the word that they represented gender. So I think it makes some sense, the arguing of the authors of the paper. So in this paper, they propose here a fine-tuned based approach by proposing BERT, which is bidirectional encoder representations from transformers, which alleviates this mention on directionality by using what they call here a masked language model, a MLM, which is not the multi-level marketing, but and this objective is inspired by the closed task. Closed task, I think he's going to talk a bit more later, but closed test basically is like fill the gap. So like, oh, today I went to the supermarket and bought some milk and eggs. I knew it was going to rain, but I forgot to take my raincoat and ended up getting wet. So kind of like that. I'll explain a bit later. And also, if you guys didn't get here, Bert and Elmo, what I said later, I think it would be interesting to say that, Sesame Street, I don't know if you guys know, but then here this guy is Bert, and then this red thing is Elmo. So it's a kid show. And then you have Ernie, and then you have, I have here the guys. Have Big Bird, Cookie Monster. So, or for Portuguese guys, Beto, Enio, Teobaldo. Anyway, so I don't know why the guys chose this, but it ended up being Sesame Street. The models are named after Sesame Street characters. Okay. So here in the end, the results that they showed, we have here like the 3 points that they think are the contributions of the paper. They say that the importance of bidirectionality for the pre-training of these language representations, because you use the data to pre-train the model, and then you have a model that can represent the inner structure of the language. And then they show that these pre-trained representations, they really reduce the need for specific architectures. So you can use this pre-trained version of the BERT, and then you use a simple fine-tuning for a downstream task. And you don't need a lot of data or a lot of computing power to do so. So it's kind of similar, the approach for transfer learning, some ways, that you have really with, convolutional neural networks and stuff like that. And also BERT advances the state of the art for 11 NLP tasks, including question answering, language understanding, etc. Okay, so for related work here, I think is one interesting part here that they put here in the unsupervised feature-based approach, is that they have like this pre-trained word embeddings. And here they mention some papers. And here you have Mikolov, which is not the Word2Vec paper, but Word2Vec is a paper indeed from 2013. And I think it's kind of fun, right? Because it's like 5 years from 5 years before BERT. Like one of the state-of-the-arts, was using Word2Vec, which is kind of like you have a shallow neural network that you have fit some context, and then you try to fit a word, and then you just use the representations generated by this shallow neural network for downstream tasks. So then you have like word embeddings, which are integral, which were really groundbreaking and really important 5 years, But then it's like 2013, and then 5 years later you have BERT, which really surpassed all the state of the art. And then 5 years we have models like ChatGPT, which it's now it's groundbreaking, not a level data scientist level, but I think now world level, right? Because everyone now is talking about ChatGPT. But I think it really shows. I think is interesting because we went from word embeddings to a thing that kind of understands language, so kind of like a huge step. Here they talk a bit about Elmo as well, but anyway, and then you have the unsupervised fine-tune approaches that you use, try to use data in an unsupervised manner. And I think this especially works well with text because we can have massive amounts of data, and depending on how you structure this data, you don't need to label the data, right? Because this is a part that's very costly, right? So I think it's really important. And then here they say the word of GPT, like Redford here. I'm pretty sure this is the one reference to GPT-1. But yeah, basically use unlabeled text to fit a model that is able to kind of understand the nuances of the language. And then here, like they say, like again, like the advantage of this approach is that few parameters need to be learned from scratch because you already have a big model, and then you fit, oh, I want to do sentiment analysis. So you can use the output of that on things. Okay. Here they argue half the part of the transfer learning. So like I said before, like you have computer vision really was the part that I think really popularized this concept of transfer learning because you have like sets of images, and then like, oh, you don't have a lot of images. You want to just classify birds, for instance. And then now you can use a neural network, the ResNet, that was trained on ImageNet, which was a huge data set with lots of features. And then like you have the convolutional layers that actually like feature extractions. And then you have the fully connected layers that you can use that to tune that for a downstream task, etc. And I think BERT kind of also is a thing that is kind of like transfer learning as well. So we can use this pre-model that's really powerful for a variety of tasks later. I think is one of the points also is that like, I think BERT is also a paper that represents this point that we get like the transfer learning age for NLP, kind of. But okay. So BERT, now they introduce the model BERT. So here they say that how it's trained, right? They have 2 steps. If I'm speaking too fast or anything, please, please let me know.
No, you're good.
Okay. Okay, so BERT is trained like 2 steps. So you have the pre-training part and the fine-tuning part. So first, in the pre-training part, this model is trained on unlabeled data. So like I said, you have text. So depending on how you mix with this text, you have huge amount of text and don't need to have someone labeling stuff. And then the fine-tuning part, you get the model that was trained with this the pre-trained parameters, and then you are fine-tuned. All the model is fine-tuned for the downstream task. So you get this model that was trained, and then question answering, sentiment analysis, etc. Okay, so for model architecture, BERT is based on transformers, like OpenGTT1 was. So have here the work like Attention is All You Need by Vaswani. And then here the transformers, and then here I think an important part is like the number of parameters, right? So BERT is 100, like BERT base, which is this kind of same number of parameters of the GPT-1s that they use to compare the results is 110 million, and BERT large is 340 million. And just, I'm going to speak about this a bit later, but just to give you context, like GPT-3 is like 170 billion. So it's like 1,000 times more parameters. So it's really huge. And then like for transformers, I'm not really going to explain transformers, but I think you have like some articles I will share later that you can explain transformers. But basically, it's a very powerful type of model, and they can present. So here is kind of like a transformer, so it kind of looks very complicated. But I think like the 3 main aspects that you can explain here that are why it's so powerful is these 3. And also another part that I think it's kind of a bit with positional encodings is that before transformers, like one of the most popular ways to train networks for NLP was like RNNs or RNN-like models, recurrent neural networks. And here they are, you use the output of the previous layer, etc. The issue here is that they are serial, right? So you can't really parallelize them. So it takes a long time to train them. So that's, I think, the main issue. But then with transformers, I think we have these three parts. So we can we can parallelize them by the structure of it. And then you have some aspects here, like the position encodings, which basically is like here, like you set like, the position of the word in the sentence, which can kind of be like this, So it's not really something that different. Usually they set like is a sinusoid that they add. They basically add this to the embedding that they use as input. And then I think the other part that is important is attention, which basically here, attention, also the work here, the attention is all you need paper. It was made for translation, basic for translation, but then the guys see that could be used for NLP and also could be used for anything, basically, the mechanism. But basically is kind of like how an input can relate to the output. So here we have a translation here. So we have like the agreement of the European zone, and then you have in French, which I really don't know how to speak, but then you can see some words here. And then you can hear like some stuff like the European Economic Area. And then like if you look the French translation, like the word order for this entity is different. It's not European Economic Zone, is La Zone Économique Européenne. So then you can see that European, it really relates to European. So the model was able to understand like economic is economic. So it was able to understand these parts. And another, yeah, and also I think it's interesting, like from La is like relates to the, which makes sense, but also it has some values like for the area, zone, because of the gender of French, like, so it's not les zones, is la zone. So I think it's able to understand these aspects of how the input relates to the output. So the transformer does not give a word by word translation. It tries to understand the aspects and then do the part that I said, like, Japanese, you have verb at the end, etc. And the most important part, I think, self-attention, the text also says that, which basically is how the input relates to itself. So basically, like here, like have the like, server, can I have the check? And then looks like I just crashed the server. So if you just see the server here, like, okay, it's the same word. But then, like, if you look at the phrase, you can see the server relates to, can I have the check? So basically is a person, right? And then like I crashed the server, so no, it's like a computer, right? So basically it's not really mathematically really far from that, but I don't know, I like to imagine that self-attention is kind of like as autocorrelation function. So it's like how the input correlates to itself. So, and I think this can have like lots of implications. So like, for instance, like for image processing, right? You have convolutional neural networks, you can extract features, but the models struggle with like, I don't know, I am holding a green notebook. So like the model, they would understand notebook, me, but also understand the aspect that I'm grasping and holding the notebook. So kind of like that. So basically we can also understand what we use as input, right? Because we also use this mechanism. Like you have the paper and you have like other resources to explain, but I think that's a very layman explanation of what a transformer is and why it was revolutionary. Okay, so like I said, here you have 340 million parameters. Okay, and then like how we input this to BERT. So they do some pre-processing, of course, and then like the first token in each sequence, they say here is this CLS token, is a classification token, which they use later for downstream tasks to, like sentiment analysis or something that can be answered like using, like a supervised learning. So is this span or not? So we can use the output of that as the input, for your model in a way. I mean, after the fine tuning. And then here, I'm skipping some parts here, but then you have like a separation token, etc. And then for a given token, its input representation is constructed by summing, the corresponding token. So the position of what this token is, the position, the segment, which they say here, like, oh, we have like the sentence A or sentence B, which is used especially on the pre-training of BERT, but also is used for other parts of BERT. I will explain later. And then finally the positional embedding. And then you have like here, figure 2. Oh, I didn't explain figure 1, but yeah, figure 1, basically here, like you have the task, unlabeled task that you have for BERT, and then you use the same model, but then we change some aspects, to question answering and other tasks. But then you go here for figure 2. So basically here we have the input, my dog is cute, separation, he likes playing. And then here we also have some aspects that they separate, right? It's not the words, they separate some parts, play and playing. So it's a different embedding when you put the tokenizer. So you run the tokenizer have like what would be like the address of each word given like this word piece embeddings. And then you have the segment embedding. So here, like, is first sentence, my dog is cute, he likes playing, is second sentence. And then the position embedding, which could be like a sinusoid on the position. So sine of 1t, sine of 2t, sine of 2e, etc. Okay. So finally, we go to the part of pre-training BERT. So they did the pre-training of BERT on 2 tasks. The first task is what they call the masked LM. So here they say like, oh, intuitionally it's reasonable to believe that, a bidirectional model is better than, a left to right or right to left. But then one of why people didn't make this before. So the issue is that if you have a left to right and a right to left, the issue would be that if depending on the task, like if you want to predict a word, like the model would be able to see itself indirectly, right? Because then you can see like left to right, and then say, oh, the word I want to predict is there, or left to right, oh, the word I want to predict is there. So you have this issue, and then like how they try to come up with a solution for that. So it's what they said, like the masked language model. So basically they mask some of percentage of the input tokens at random, and then they use this closed task, like the similar to closed task, which I showed earlier, is like the fill the gap. So you have the word, and then you use a masked token. And then they go here to go a bit about the masked token, that the masked token does not exist in the embeddings, but then they do some random, like, oh, they show a random word, etc. So basically that's the idea. You mask the words so you don't have like this similar kind of data leakage, I suppose. Then the second task that they use for the pre-training is what they call next sentence prediction, which could be similar to question answering, because you have to understand the context of language, natural language inference. So basically the idea here is that to see if this model can understand like if this is a coherent test or not, basically they pre-trained this next sentence prediction. So you see like, oh, the penguins are a type of bird, and then like they live in the Arctic. I don't know. Okay, so it's next sentence. The penguins is a type of bird. Bob went to the mall. So it's not the next sentence, right? So it's kind of like that. So here, like, 50% of the time is the actual sequence or not. So they have this task here that is next or not next. Okay, so then the pre-training data here. So they use here this book corpus, English Wikipedia. And I think one part that they highlight here that I think is important is that like it's critical to use a document level corpus that shuffle sentence level in order to extract long contiguous sentence. So I think this is kind of important, right? Because they want, it's like a language model. So they want something that's like for documents. So it's not just some sentences, right? Because then maybe the model won't understand the sentence and not understand that, have documents that have a larger structure and stuff like that. Okay, so finally, after you do the pre-training, you have the fine-tuning part. So the fine-tuning basically is the specific task that you have BERT. So basically here, like, and that they go. So squad, glue, and other tasks that they use to compare the results. So basically here for BERT, they have like for each task, we simply plug the task-specific inputs and outputs on BERT, and then they change some parts. So for instance, like this aspect, like sentence A or sentence B, could be, the sentence pairs in paraphrasing. So the text is the phrases, or, the hypothesis, premise, entailment. So like, oh, this hypothesis entails on that. So yes or no. So you can use these sentence embeddings to understand that. Or in question answering. So have sentence A is question, and sentence B is the context that can be used to answer this question. And so on and so forth. And then like you have this first embedding that they say here, the CLS, could be used, for tasks like, sentiment analysis, etc. Right? So it's like use this, and then like, oh, it is good or not. Yeah, it's good sentiment, etc. I think another point that's pretty important of this work and why it's so popular is that compared to the pre-training, fine-tuning is relatively inexpensive. So here they say, like, for these data sets, it didn't took too long to train the model. So I think, and also it didn't require anything close to the data that was used to be trained. So here, like 100, 200 millions. And then I think there's some questions, like 1,000 questions, I think Squat was. So really far from, is another, the size of data sets, is another dimension. Okay, so then finally the experiments that they have. So first they have the GLUE one that is known for General Language Understanding Evaluation Benchmark. So it's a collection of diverse NLP tasks that they used. So I think here, yeah, I have this one. I will share with guys all these things here. I have this. But then I have GLUE. So here, like just to give you guys context, so I think I can read. So have like grammatical, so like, oh, it's ungrammatical, or similarity, if it is answerable or not, the entailment, if it's ambiguous, contradiction, question similarity, etc. So it's a set of data sets. They have different tasks, and then you have to predict each task. So okay, I think that explains. Okay, so fine-tune GLUE, they represent the input, like I said, and then you have the final hidden vector. They use the CLS token as the aggregate representation for the downstream task. And then the results they show here in this table, and both BERT base and BERT large. BERT base is the one with similar size to GPT-1, and BERT large is a larger version of the model. So they outperform all systems by some margin. And here they also said, note that BERT base in OpenAI GPT-1, which was not known that would be the one, they are nearly identical on the size of the model. So here you can see that pre-OpenAI state-of-the-art, it was 80%, average was like 74. They have different metrics, right? So it's a bit hard to what unit is this, but anyway, BERT base, you had 79 and then 82, so it was a huge increase on the leaderboard, really important, and also increase over OpenAI GPT, so really interesting. Then they show Squad 1, which is the Stanford question answering dataset, which is a collection. Okay, it's 100K. Okay, it's kind of large dataset, but it's not million still. But they are crowdsourcer question and answer pairs. So, okay. So basically, they do like the part how to perform the model. I think it's interesting here. They show the results for Squad 1. And then here, I think it's interesting that you have BERT like 87 and 92%. Oh, no, it's F1 score, so it's 92 F1. But then I think it's interesting that, okay, beats state of the art, but also beats humans. I mean, so it's kind of like it better, has better performance than a human level, so kind of interesting. But also because Squad is kind of a simple data set, that's why they released Squad V2 that extends the Squad V1 problem definition, but they allow the possibility that no short answer exists in the paragraph. So it's a bit harder, right? Because then, like, for instance, let's say that you give a context and the answer is not there. So the model, instead of just guessing, which he could in Squad 1, he had to acknowledge and maybe say, maybe output, not say, but like, oh, there's no answer. So it's a bit more realistic, right? Because then you random guess, like you can guess, you will be right sometimes, right? And then you have the results here for Squad 2, which again, I think it makes sense. Humans are really have a, they are better than BERT. But I think it's interesting to see, like, if GPT-3 and OpenAI, ChatGPT, how they fare this. I think they should be kind of good. Maybe they surpassed human performance, right? Because they can test, MBA tests and so on and so forth. So maybe 5 years we got this superhuman on question answering, and maybe 5 years more I don't know where we'll be. Anyway. Yeah. So yeah, okay. But you see that again, like it increased the results, previous best results. And then you have SWAG, which is common sense, data set for common sense inference. And then like here again, like they use the CLS token as representation, which is softmax layer. And then again, for this test for common sense inference, you can see that the 5 annotations is better than BERT, but I think it's pretty safe to say that at least BERT large achieved human-like performance. So really interesting, especially like if you see other models here, like it's 69, I mean, 59, really increase. I mean, the Transformers architecture, because also has this big gap from OpenAI GPT, but there are also another large gap for BERT large. Okay, and then finally they get to the part of ablation results, which is kind of like they remove some parts of the model and see how the performance works and how the performance is deteriorates and so on and so forth. Which I don't know. The first time I see this word was in this paper. I remember the first time I read it, and I don't know. And if you look at Google, it's like they show some like medical stuff. Anyway, so basically they remove some aspects to see the evaluation performance. So like the importance of this bidirectionality of BERT and these two tests, like the masked language model and the next sentence prediction. So they fit BERT base, and then they fit other versions of BERT. So have like this no NSP. So it's a bidirectional model that don't have this next sentence prediction task. And you have the left to right and no next sentence prediction. So they fit these models, and then they use on these other data sets. So have these are glue ones. Yeah, because it's glue one's task. So have like questions, have like answerable, contradiction, etc. And then you have here the results. And I think I highlighted the ones that have a huge gap, I think. So I think like for next sentence prediction, they have a really huge gap in this Q and LI, which is answerable question, if a question is answerable or not. Yeah, well, I think it makes sense, right? Because then you have the two sentences, and maybe the correlation between them, I think, really helps. Like if it's a question is answerable or not, it's kind of similar to, is the sentence similar to that one or the other? Well, okay. But then you have the left to right, or would be like the non-bidirectional model. You can see like in most tasks, I mean, of course, these I highlight the ones that I think are huge gaps, so it's not very scientific of me, but I think like 10% here, 10% here, no, 10 F1s here. But anyway, I think it's really like the next sentence prediction in some instances is really important, but I think this bidirectionality for most tasks you have a huge degradation of the values obtained, right? And then here the hierarchy of our squad, it's intuitive that left to right model will perform poorly because, question answering, so it'd be good to understand the context of the question or what words you trying to refer in your question, which makes sense here because the squad was one of the ones that have one of the hugest decreases in performance. And then finally, they go to effect of model size. And I think here, they have this huge models. And I think I highlight two parts of this text. This first one is, however, we believe that this is the first work to demonstrate convincingly that scaling to extreme model sizes also leads to large improvements on very small scale tasks, provided that the model has been sufficiently pre-trained. And I think this is funny because, they say here, extremely sizes, right? And then it's 300 million parameters. And then you have GPT-3, which 107 billion parameters. So I think what they say here really makes sense of what the future did, right? Huge models did improve the results, especially if you have, even though if it's a small scale task, given that the data that you used to fit this pre-trained version of the model was sufficient. And then here again, here they ask one example that they mentioned that, they increased the hinting dimension from 200 to 600 helped, but then they increased to 1,000, did not bring further improvements. And also I think is that also because of, also depends on how complex and the size of the data set that you have, right? Because depends on the model, you don't have, especially for, I think, supervised learning problems that you have the labeling issue. If you have a huge model, you can increase, the number of layers and stuff like that. But I think eventually we will start fitting noise, because the model is so huge that you kind of can't extract more from the data, right? But then these unsupervised models, I think they can't do that. Anyway, but then here again, both of these prior works as a feature-based approach, we hypothesize that when the model is fine-tuned directly on the downstream tasks and uses only a very small number of randomly initialized additional parameters, the task-specific models can benefit from the larger, more expressive pre-trained representations, even when the downstream task data is very small. So I think it's really what happened, right? With all these models, GPT and all the other Google models, which are not that popular, I think, is this, you have a huge model and then GPT, do that, and then fine tune. You don't need lots of examples to fine tune the model and stuff like that. So I think they said that in 2018, and 5 years later, it really makes sense, especially this part of extreme model sizes, because GPT-3, for instance, we are training a data set 8 million words, I guess, and then GPT was trained I think it was almost the entire internet, So more data, more size of model equals more powerful in this case. And then I think another part I think is kind of interesting is you can also apply not just for the fine-tuning BERT, but you can also do the kind of feature-based approach with BERT, which basically you use the output of a BERT, a pre-trained BERT on these, the two tasks, the masked language model and the next sentence prediction, and use the output of that. You don't fine-tune BERT, but you use the embeddings extracts for the layer to fit on your downstream tasks. So here they say, however, the feature-based approach, fixed features are extracted. And then they say here that maybe have some benefits, right? Because you have some, maybe you don't need to compute, or maybe the data doesn't really fit with BERT, like you said, you have to fit what is sentence A, what is sentence B, do you use the CLS token or not, etc. So basically here to test this, they train the BERT and then they extract some of the layers. Some of the, I will share guys later, but you extract some of the layers and then you apply a bidirectional LSTM model to this. And then you get kind of good results. So here we have some like for some, for this name denier task, so name entity recognition. And then you can see like BERT base achieves, 96 F1. And then if you have like, if you instruct the embeddings, second, the layers, and then if you concat the last 4 hidden layers, you have 96.1, which beats Elmo, which was state of the art. And then the other ones, I mean, apart from the embeddings one, all the other ones are kind of comparable. So it's really interesting. So you don't need to fine tune BERT to get good results. You could also use only extract them, right? So finally, the conclusion, which I highlight everything, but basically, like you say, like I have these improvements on transfer learning. So you can use these models for you can have a pre-trained version of BERT and then fine tune to your model, and you don't need like lots of resources to do that. Another point is this bidirectionality that they put. So this how the model was able to pre-train. Really improve results over, for instance, OpenAI GPT-1. And I think also the main aspect of this is that it kind of release the Kraken, of models for GPT, BERT-like models. So you have stuff like they call here like BERTology. And also you have stuff like Hugging Face, a site that have lots of models that you can see and you can try out. I did that for the prompt engineer case, but basically here BERTology. So it kind of released a field on science, let's say. So have your paper here like a primer in BERTology. So here they go on and try to understand several versions of BERT. So have here like and all of them have the names, right? So we have Distill BERT, Owlbert, QBERT, which is, it's not a Sesame Street, but it's a game. I don't know if you guys have played this, but anyway, so we have several different models that were released that are BERT-based or similar to BERT for different types of tasks. So even for Portuguese, so you have a Hugging Face, you can go here like you have Bertimbau, which is okay. It's the Brazilian version, so which was trained by the guys from Neuromind, from Professor Lotufo. Also, you can go here and do stuff. Computer Hugging Face, I do recommend if you guys are interested. And then here you have Camembert, which is Camembert like cheese, so it's French, right? And then you have other models here, so you can see like you have Ernie. So Ernie Inoue has a model. So yeah, this guy also is a model, which is a Chinese BERT. Okay, and then you have Big Bird. Big Bird is also a model. Big Bird is also a model. So Big Bird is also a model for some reason. Maybe they have Cookie Monster. They don't have Cookie Monsters. Well, if we release a model, we already have the name, so we have just to fit the acronym. Anyway, so here I also asked ChatGPT, add like the models. I think it's really interesting as well, right? So I write some famous LLM models with the year and number of parameters. So here we have BERT, 300 million, and then you have Roberta from Facebook, which it's a larger version. We also have some stuff that tries to go against this increase of number of parameters like distillation. So we have Albert and Distillbert. We have lesser parameters. But then the powerful ones, we have XLNet. GPT-2 is 100 billion, but then GPT-3 is like in the realm of hundreds of billions. And who knows how much is ChatGPT or GPT-4, so yeah, I think basically that's it. And also, I think just to end the paper, I think lots of people are talking about, ChatGPT is going to, end Google, etc. and stuff like that. But I mean, you have like this news like before, right? Like this cloud engineer that the Google chatbot is sentient, like Lambda, right? Which I don't know, like if there is a company that has resources, smart people, and data, I think Google is a good company that have all of these three aspects, because this is what I need, right? We need huge computers, huge data sets, and no smart people to develop this structure. So I don't think it's going to be the end of Google. And also I think it's interesting parts I forgot to add, but BERT, I think it's kind of used for most of the, nowadays is used for most of the English queries on Google when you try to search. So they use BERT, which is better than just getting the words. So for future models, they can use that for the input of this. And I think that's it, guys. So thanks, everyone.
All right, nice. Thank you, Matheus. Teams. I think Google already has the model. They are just waiting for search integration, maybe.
Yeah. I mean, like I don't saw the videos of this guy, but I think
Oh, I listened to a podcast with this guy.
it was a guy that was fired from Google because he said this AI is sentient, like
no, he was fired for some. He was not fired. He was put on leave as far as I remember for some other issue that he reported.
Yeah, but then he said this thing, right? So, but yeah, I think like they should have like or they are working on it.
Really interesting to listen to a podcast with him explaining his reasoning behind why he thinks he's sentient. I do think that he's extremely biased due to his. I don't know if anyone had listened to it or knows some about this guy, but he's really into some mythology and like he's so the way he presents.
I really
very
don't.
very biased to he would be the perfect person to think that AI is like.
I really don't believe this stuff. Like, I really don't. I mean, it's my position. I really don't believe we are close to general AI or stuff like that. Because these models, I think, fitting models is kind of like interpolation on your data. And also, you have so much data, these models, and they are so deep that they are kind of able to do creative interpolation, right? Like ChatGPT will say, like, explain data science like a gangster. And they are able to understand what gangster is, what data science is, and then, hey, buddy, data science is statistics. So it's
I don't think that GPT is creative. I wouldn't say. I was trying to make it creative stuff, and it's extremely hard project. And asking GPT, "Are you creative?" and he would blankly say, "No, I'm not creative. I cannot create stuff from you." He can mimic some stuff, but in the end, there's also some creativity and comedy. That was my first. I was trying to make really funny jokes. It is not a structural because he's very expert in understanding language structure, but not really expert in understanding stuff that is a context and how do you say this above language. Irony. Irony is not on text. You need to have some other context to be able to understand that. It doesn't get irony.
Yeah, and another thing that I said, like here, is like the number of parameters of the models, right? Oh, Fabio is going to say something, or someone else. I don't know. Oh, no.
No, and about sentience, like what is to be sentient? Like the model is there, stopped until you just like throw some inputs into it.
Yeah.
How would this sentient
actually
be?
No, but maybe so. But it's a completely different discussion than since I don't think that maybe is that far, but because maybe if you have a function that keeps like have some kind of free will, if it continues to generate random correlations and continues to push it forward, maybe it would. Why do humans want to do stuff? It has some tricks, and as far as I know, it's very hard not to think about nothing. So we have some kind of biological function that keeps pushing thoughts to our brain, and maybe this is what makes us come up with stuff. And the difference is like GPT doesn't have a function that keeps feeding random thoughts to it.
Yeah, but like if you go and put it in a reinforcement learning like setup, and like have the steps to be 1 second, I don't know, and then like it reads like the environment, use it as input, and gives you like its output.
Yeah.
Is this sentient?
I don't know. Maybe they start.
How are we going to say if it is or
It's very
isn't?
hard
I don't
to-
know. I don't have a clue.
There is
Like,
no proper definition of consciousness.
there's no proper definition. Yeah.
Yeah, but I think it's interesting. I think that the point here is that like 2013, Word2Vec, 2018, BERT, 2023, like ChatGPT. So it's like what will be like in 2028, right? Because like we like discover another architecture that maybe improves on transformers, or maybe like we'll have like just big size, have a trillion parameter model that will be like just a few companies in the world will be able to handle it. It's kind of like OpenAI does, right? Because we only access via API. So will be that the future, because then like you have lots of power for a few companies. So I think that's a provocation on my side here, because then in the end you have like these huge models that you only have requests via API, stuff like that. So and they will be so powerful. But yeah, and also I forgot, I'm going to put on Paper Club, but also if you like guys like, they has this blog from Jay Alamar. I have this one for research from Google, it's kind of good, but also has this Jay Alamar. They have a blog post that explains BERT. So I think it's, figures, maybe it's easier to understand some aspects. So here, like how you track BERT, tasks, side of BERT, how it does classification. Explain Elmo as well, which I didn't. OpenAI 1, GPT-1. And then you have, I will post you guys on this blog post because I think it's an interesting reference. And also, if you guys is interested, you have Hugging Face, they have models and stuff like that you can try. It's really interesting. So I have like GPT-2, and then some of them have posted interfaces. So wait, so my name is Thomas, and I am a bank engine. I live in St. Louis. He doesn't know Thomas the Tank Engine. But yeah, you can test some stuff, and then they show here how to use in Python. So if you guys are interested, you guys can easily take a look, do some tests and stuff like that. And also GPT-2, but they also have BERT and other version of BERT. I mean, NeuroMind here. You have here like can test here. So yeah, basically that's it. So
All right.
Okay, can stop presenting, guys.
Okay, let me stop recording.